Hi, welcome to Lecture 7 of the online course on Explainable Machine Learning and Artificial Intelligence. This is the second lecture in a series of 2 on model-agnostic post-hoc explanation methods. The goals of the second lecture will be to continue reviewing the most common methods for generating model-agnostic post-hoc explanations, examine how the different methods relate to each other, and finish by discussing the strengths and limitations of model-agnostic methods. In Lecture 6, we covered individual conditional expectations, partial dependence plots, and the local surrogate, also known as LIME. In this lecture, we will turn to 3 other methods: Shapley values, SHAP, and counterfactuals. Let's start with Shapley values. Shapley values are a concept developed in the general field of game theory. In the recent years, this concept has been applied to machine learning with the purpose of generating post-hoc explanation. Before diving into the details, let's start with some motivation on what Shapley values aim to achieve. Let's go back to the most fundamental example of an interpretable model: linear regression. In linear regression, the output is obtained by multiplying every input feature by a coefficient beta, summing over the features, and possibly adding an intercept term, beta 0. In this model, the contribution of feature j to the output is directly given by multiplying the value xj of this feature with the corresponding coefficient beta j. This is a quantity that we also called the effect of feature j in the lecture on linear regression. If the feature is not mean-centered, then it is natural to compare the effect beta j xj to the effect of the mean, beta j multiplied by the mean of xj. We will call phi j this contribution of feature j. Clearly, phi j depends both on the model f, because it depends on model parameters, and on the instance and x we are looking at. Now, if we sum the contributions phi j of all features to one instance x, the total we get is the difference between the output of the model for instance x and the average output of the model over all instances. So this is a nice property of this definition of contributions in a linear regression model. The sum of contributions is directly the difference with the average output. Shapley values are a generalization of such a definition of feature contributions beyond linear regression to black box models that are intrinsically nonlinear and possibly include interactions between features. So, Shapley values are a model-agnostic post-hoc explanation method for black box models that was developed by translating concepts from game theory to the machine learning setting. We will not go into the details of game theory here, but only cover the main ideas. Within game theory, Shapley values are a method for assigning payouts or gains to players, depending on their contribution to the total payoff in the game. Strumbel and Kononenko propose to translate this setting to machine learning by considering the prediction for a single instance of a dataset to be a game. In this game, the gain is the difference between the actual prediction of the model and the average prediction, obtained by averaging over all instances. In this interpretation, the values of different features correspond to players in the game. A key concept in game theory is that a player can join the game or not. Translating this concept to machine learning, a feature joins the game if its value is included in the computation of the output. Finally, the Shapley value is defined formally as the marginal contribution of a feature value, averaged across all possible coalitions, where a coalition is a combination of a set of features that have joined. An intuitive way to understand the Shapley value is the following illustration. The features enter a room in random order. All features in the room participate in the game, meaning that they all contribute to the prediction. The Shapley value of a feature is the average change in the prediction that the coalition already in the room receives when the feature joins them. An important aspect of Shapley values is that they provide a definition of feature contributions that satisfy a set of formal properties, also called axioms. The first property, and probably the most important one, is called efficiency. This property states that feature contributions, summed over all features, add up to the difference between the prediction for x and the average prediction. This is the property of linear regression that we started from and which we wanted to generalize to any black box model. The second property is symmetry, and it states that the contributions of two feature values should be the same if they contribute equally to all possible coalitions. The third property is called dummy. It says that if a feature does not change the predicted value for any coalition, then it should have a contribution of 0. And the final property is additivity, and it states that for a game in which the output is equal to the sum of two games, the respective contributions should add. A key point is that game theory ensures that Shapley values are the only definition of feature contributions that satisfy all four axioms. So Shapley values have a nice theoretical property, but concretely, how do we compute them? Game theory gives an explicit but somewhat complex formula for Shapley values. Here is the formula for the Shapley value of feature j called phi j. Phi j is given by a sum over all coalitions not including feature j, meaning all subsets S of the full set of features minus feature j. Each term in the sum contains the difference between the value of the subset when feature j is added to it and the value of the subset without the feature j that we are trying to explain. This difference is multiplied by a combinatorial normalization factor that depends on the number of features in the subset S and the total number of features P in the input. Now, what is the value of a subset S? It is the output of our black box model F applied on the values of features in the subset S and marginalized over all features not present in S, to which we then remove the overall average output of the model. For example, if we look at the subset S consisting of features 1 and 3, the values of features 1 and 3 are fixed to their values in the instance we are considering, indicated as small x1 and small x3, and the values over features 2 and 4 are integrated over. In general computing the Shapley values is in principle a difficult combinatorial problem, but Stromberg and Kononenko developed a Monte Carlo sampling approach that can be used to evaluate them in practice. To make this complex definition of Shapley values a little more concrete, let's illustrate it with a toy example taken from the Interpretable Machine Learning book by Christoph Molnar. In this toy example, we have a black box model that predicts the price of an apartment based on whether there's a park close by, what is the size of the apartment, what floor it is on, and whether pets are banned or not. Imagine the model takes as an input a specific instance, a specific apartment that is close to a park, has a size of 50 square meters, is on the second floor, and pets are banned. For this instance, the model predicts a price of 300,000 euros, while the average prediction in the neighborhood is 310,000 euros. The goal of Shapley values is to explain the contributions of different features to this difference between the prediction for this specific apartment and the average prediction. Let's look specifically at the contribution of the fact that pets are banned. To compute the Shapley value of the feature pets banned, we need to compute its contribution to different coalitions with different feature values. Let's, for example, evaluate the contribution of Pat's band in a coalition with park nearby and 50 square meters. For this, we will look at the difference between the prediction for two instances. One for which pets are banned, and one for which pets are not banned. In this example, this difference is 10,000, so the band contribution is 10,000. Note that we are fixing the park nearby and apartment size features to their actual values in the feature we want to explain. But we have a fourth feature, apartment floor, which is not included in the coalition. Because it is not included in the coalition we're considering, we need to average over this feature, and in a Monte Carlo approach, this is done by replacing its value by values from random dummy instances. So this is the contribution of Pat's band to a specific coalition. To compute the Shapley value, we need to look at all possible coalitions. For this example, all the possible coalitions are listed here. First, the coalition with no other features. Then coalitions with one feature at a time, coalitions with two features at a time, and finally a coalition with all features. This is of course a toy example, but what it demonstrates is that in general, the number of coalitions is exponential in the number of features. So if we have many features, computing the Shapley values become computationally very demanding. To summarize this part, Shapley values have a number of advantages. They provide a method for generating model-agnostic explanations that is based on strong theoretic principles of game theory. A key property of Shapley values is the axiom called efficiency, which ensures that Shapley values provide a fair distribution of contribution values over features, and therefore a full explanation of the output of the model. Shapley values are contrastive in the sense that they directly provide an explanation in terms of a comparison with the average output. The main disadvantage of Shapley values is that computing them is very computationally demanding if the model uses many features, since the number of coalitions to consider increases exponentially. A second disadvantage is that Shapley values do not provide a sparse selective explanation unless the black-body model is itself sparse. Finally, computing Shapley values actually requires access to training data. We will now move to the next method in our list of model-agnostic methods for post-hoc explanations. The next method is called SHAP, and it is in fact closely related both to Shapley values, which we have just discussed, and to Lime, which we covered in the previous lecture. SHAP is probably one of the most popular methods for generating model-agnostic post-hoc explanations, and part of the reason for this is that the code is fully available online and provides a very user-friendly interface for generating attractive graphical explanations. The code and documentation for SHAP are provided on the two links listed on this slide. The graphic on the left illustrates a black box model. The graphic on the right illustrates the type of explanation SHAP generates for the output of this black box model. In the following, we will go through how SHAP generates explanations and what precisely is the explanation shown here on the right. SHAP is an acronym that stands for Shapley Additive Explanations. It's a post-hoc explanation method introduced in a paper by Lundberg and Lee in 2017. And an important aspect of this method is that it unifies Lime and Shapley values. More specifically, SHAP is based on a set of key ideas. The first one is that SHAP builds a local explanation model of a black box model around an instance X, and this is very similar to the approach introduced with Lime. The second idea is that this local explanation model generates additive feature contributions. Finally, these feature contributions satisfy a set of properties which are very similar to the axioms for Shapley values. More specifically, starting from a specific instance X that we want to explain, SHAP generates a locally linear model that acts on simplified features. So the output of SHAP is a linear explanation model G on a set of simplified features Z prime, which are defined by a mapping onto the original features X prime. These simplified features are defined in such a way that if Zj prime is 1, then the original feature Xj prime is equal to its value into instance X that we are explaining. If Zj prime is 0, then the original feature Xj prime is equal to the average of Xj over the dataset. In this linear model, each linear coefficient directly provides the contribution of the feature to the output, and these are the explanations produced by SHAP. The intercept in the local linear model is equal to the average output of the black box model F over the whole dataset. Similarly to Shapley values, SHAP is based on a set of desired properties or axioms. The first desired property, and perhaps the most important one, is called local accuracy. It states that the output of the local explanation model when all inputs are equal to 1 should be equal to the output of the original black box model for the instance of interest. Recalling the definition of the local explanation model, that means that the output of the black box model is equal to the sum of SHAP feature contributions plus the intercept. But this intercept is the mean value of the black box output over the whole dataset. This implies that the sum of SHAP feature contributions over all features is equal to the difference between the black box model output to instance X and its averaged output. So this local accuracy property is directly equivalent to the efficiency property in Shapley theory. In addition to local accuracy, SHAP values satisfy two additional properties called missingness and consistency. I will not go into the details of these properties, but Lundberg and Lee showed that they are equivalent to the symmetry, dummy, and additivity properties in the original Shapley theory. So, similarly to Shapley values, altogether these three properties ensure that there is a single solution for SHAP values, and this solution is given by Shapley theory, applied in the context of local linear models. So, Shapley theory gives us a formula for SHAP values, the coefficients in the local linear explanation model. This formula is written here. It is very similar to the formula we discussed earlier for classical Shapley values. It is a sum over all coalitions, defined as subset of simplified features Z that are set to 1. Each term in the sum contains the difference of conditional means when feature I is included or not, and this difference is multiplied by a normalization factor. When introducing SHAP, I said that it was closely related to Lime. But what exactly is this relation? To understand the relation between Lime and SHAP, let's go back to the definition of Lime. Lime built a local linear model close to the instance of interest, and this is very similar to SHAP. However, remember that Lime built this local linear model by optimizing the loss function written here. In particular, this loss function depends on a weight kernel called pi. In Lime, the choice of this weight kernel is made based on heuristics rather than theoretical principles. As a result, the obtained local linear model will depend on this choice, and it will in general not satisfy the three properties we listed for SHAP. Instead, SHAP generates a local linear model that is the result of linear regression with a specific kernel given by the set of normalization factors determined by Shapley theory. So SHAP is equivalent to Lime, but with a principal choice of weights for the linear regression. An important issue with SHAP is, however, that corresponding linear coefficients are still numerically hard to compute, because they are based on combinatorics similar to Shapley values. More recent work by Lindberg and colleagues has, however, addressed this problem. They developed specific, highly efficient algorithms for computing SHAP for tabular data when using tree-based black box models such as random forest, gradient-boosted trees, and others. This algorithm allows for an exact computation of marginal perturbations, which are in general NP-hard, but become polynomial for tree-based models. Because it is highly efficient, this algorithm can then be used to build global explanations from local ones. Let's look at a concrete example of SHAP on a classical dataset, the California housing dataset. This example is taken directly from the implementation of SHAP available online. Here, the goal is to predict home prices based on 8 features: median income, median house age, average number of rooms and bedrooms, the population and average occupation in the block, and the geographical location given by latitude and longitude. We can train a tree-based black box model on this dataset, for example, a gradient-boosted tree. And then we can use SHAP to generate explanations for the outputs of this model. Here's an example of the output of SHAP for one given instance in the dataset. For this instance, the output of the model was 3,175, while the average output over the dataset is 2,068. SHAP provides an explanation for the difference between the output and the average output in terms of a list of feature contributions sorted from the highest to the lowest when going from up to down. In this case, the highest positive contribution is due to median income, followed by longitude, which was, however, offset by a negative contribution of latitude. Importantly, because of the property of SHAP that we called local accuracy, the sum of contributions of the different features sum to the difference between the actual output and the average output. And this is exactly what this figure illustrates. This is an example of a local explanation for one given instance. We can then generate many such local explanations for different instances in the data and use them to build global explanations. The SHAP summary plot provides one type of such global explanation. In this plot, each point is a Shapley value for one feature and one instance. Different lines show Shapley values for different features, jittered in the y direction to show distributions. The width of these distributions quantify the strength of SHAP values over the whole dataset for each feature. So this plot shows that over the whole dataset, latitude and longitude play an important role in the outputs, followed by median income and average occupancy. The color code shows the values of the feature for the instance, rescaled between low and high. So in general, low latitude and longitude, shown in blue, have positive Shapley values and therefore a positive contribution to the output. In contrast, for median income, positive values, shown in red, have positive Shapley values, as one would expect. Another type of global explanation is provided by SHAP dependence plots. These plots show for each instance the Shapley value as function of the feature value. The plot on the left shows Shapley values as function of latitude, and we see again that latitude has a strong negative influence on the output. The color code here shows at the same time the longitude for each data point, and we see that latitude and longitude are strongly correlated in this dataset. The plot on the right shows Shapley values as function of medium income, which, as expected, has a strong positive influence on the output. The color code here shows that there are no correlations between medium income and average occupancy. So SHAP dependence plots give us a global explanation of the role of different features in the model in a manner very similar to PDP and ICE plots that we discussed in the previous lecture. To summarize, SHAP has a number of advantages. It is based on theoretical principles similar to Shapley values. It is directly connected to LIME, which provides a more direct interpretation than Shapley values. An efficient implementation is available for tree models, so it is easy to use and generates attractive plots. The main disadvantage is that some versions of SHAP may require the full training dataset. Let's now turn to counterfactuals, the final method in our list of model-agnostic post hoc methods. First of all, what is a counterfactual? Let's start with a very concrete example. The statement, "If I hadn't taken a sip of this hot coffee, I would not have burned my tongue." Following a real situation, I burn my tongue, this statement imagines an alternate sequence of causal events in which this outcome would not have occurred. So this statement explains how the outcome of the sequence of events could have been changed. This type of statement is what is called a counterfactual. A key idea is that counterfactual statements can provide us with a different type of explanations for the decisions produced by machine learning models. More specifically, providing counterfactual explanations provides us with a way to address the right to explanation for data subjects. Indeed, the counterfactual explanations can inform and help understand why an outcome or decision was reached, provide grounds to contest adverse decisions, and most importantly, help understand what the data subject or end user could change to receive a desired result. More specifically, a counterfactual is a causal statement of the type, if X had not occurred, Y would not have occurred. So it's a statement that links a cause to an event, and in that sense, it's an explanation of the event. Within explainable machine learning, an event is the predicted outcome of a model for a given input instance. And causes are feature values that led to this prediction. The goal of a counterfactual is to explain how the prediction can be changed. But the requested prediction change needs to be defined by the user. The user specifies what is the desired outcome. So a counterfactual states when the prediction changes for the desired one if inputs are changed. Or more specifically, what is the smallest required change in the inputs to obtain the desired output? Very concretely, a counterfactual explanation is a new input instance that does not necessarily belong to the original dataset. Let's look at a concrete illustration of the use of counterfactuals in machine learning. We will focus on a specific task, the prediction of credit risk by a machine learning model. Here, the input features are quantities such as the requested credit amount, duration, and purpose, as well as the characteristics of the person who applies. So a person typically requests a credit of a given amount, duration, and purpose. Then these data are given to a machine learning model. If the model rejects the credit application, the applicant wants to know why. And more specifically, what are the actionable options for them to change the outcome? What can they change in their application to increase the chance of getting the credit? Ideally, a counterfactual explanation would tell a person What is the smallest possible change in the input feature values? And this change needs to be actionable. For example, a counterfactual that says, if you had more savings, your credit would have been approved, is not very actionable and therefore not very useful. Instead, it would be much more useful to have a counterfactual saying how much the credit amount and duration need to be changed for the credit application to be approved. An important property of counterfactuals is what is called the Rashomon effect. Rashomon is a classical movie which starts from an event, and this event is then explained independently by different people. The key point of the movie is that each person gives a different explanation of the chain of events that led to the final outcome. Essentially, each person gives a different counterfactual explanation. Within explainable machine learning, the Rashomon effect corresponds to the fact that there can be multiple different counterfactual explanations. Each of them tells a different story and proposes a different path of action. These counterfactual explanations can even be mutually contradictory. In general, having multiple counterfactual explanations is a good thing, as it may give multiple possible paths of action to the subject for whom the counterfactuals are produced. So within explainable machine learning, generating multiple diverse counterfactuals is one of the goals. More generally, researchers in explainable machine learning have identified a set of desired properties that counterfactuals should have. The first property is that the output change requested by the user should be produced as closely as possible. The second property is that the generated counterfactual instance should be as close as possible to the original feature values. More specifically, to be actionable, counterfactuals should change as few features as possible in the original instance. This can be thought of as a form of sparsity in counterfactuals. The third property is that the algorithm producing counterfactuals should ideally generate multiple diverse counterfactual explanations so that the user has a number of different options from which they can choose the actionable one. Finally, counterfactuals should have feature values that are realistic and likely to occur in real life. Otherwise, they would not be actionable. Several studies have developed algorithms that generate counterfactuals based on these desired properties. The general approach is to write a loss function that encapsulates the goals and then generates counterfactuals by optimizing that loss function. Here we will cover only one example, an approach developed by Wachter and colleagues in a 2017 study entitled Counterfactual Explanations Without Opening the Black Box. In this study, the authors proposed the loss function written here. Here, L is the loss, X is the original instance, X prime is a counterfactual instance, Y prime is the desired outcome of the black box model, and lambda is a parameter. X and Y prime are inputs to the algorithm, and X prime, the counterfactual, is the output, which is obtained by optimizing the loss function. The loss function consists of two terms. The first is the distance between the desired outcome Y prime and the counterfactual outcome, meaning the output of the black box model F in response to the counterfactual input X prime. Minimizing this term ensures that the requested output Y prime is produced as closely as possible. This was the first desired property that we listed for counterfactuals. The second term in the loss function is the distance between the original and counterfactual instances. Minimizing this term ensures that the counterfactual instance X prime is as close as possible to the original instance X. The distance used here is a form of L1 distance, which ensures that the difference is sparse, meaning that the smaller possible number of features have changed between X and X prime. So minimizing together the sum of these two terms addresses the desired properties 1 and 2 from our list. Clearly, there's a trade-off between the two terms. Minimizing the second term would lead to x prime equal x, but in that case, the output of the model would not change the desired value. So adjusting the parameter lambda allows to control the trade-off. Other, more advanced algorithms have been designed in other studies to include the properties 3 and 4. Let's now look at the algorithm that optimizes this loss function to generate counterfactuals. The first step is to select the instant x to be explained, the desired outcome y prime, and the tolerance epsilon, which will be used together with the parameter lambda to control the trade-off between the two terms in the loss. The second step is to sample a random instance as an initial condition. The third step is to optimize the loss function in the vicinity of the initial condition. Then the optimization is repeated while decreasing lambda until the difference between the counterfactual output and the desired output is less than epsilon. And this full procedure is repeated multiple times from different initial random instances to generate a list of counterfactuals. Let's now look at a concrete example where an optimization algorithm has been used to generate counterfactuals. This example is taken from a 2020 study by Dendel and colleagues called Multi-Objective Counterfactual Explanations. This study developed a more sophisticated algorithm for generating counterfactuals that optimized all 4 desired properties that we listed. This algorithm for counterfactuals was applied to the German credit dataset. For this dataset, the goal of the machine learning model was to predict the credit risk of an applicant based on a set of input features. The output is simply binary, either good or bad credit risk. The model used for this prediction was a black box model, a support vector machine with radial basis kernels, which gave as the output the probability of a good credit risk. Here is an example of an input instance in the model. The features consisted of the characteristics of the applicant, age, gender, type of job, type of housing, the amount of savings and checkings. The last 3 features on the right correspond to the requested credit, the requested amount, duration, and purpose. For this input instance, the probability of good credit risk returned by the black box model was 0.41, which is lower than 1/2, so it implies that the credit is refused. Of course, ideally, the desired outcome for the applicant is that the credit is granted. So Dendel and colleagues used their algorithm to generate counterfactuals for a desired outcome, which was that the probability of good credit was larger than 1/2. They generated 82 counterfactuals, summarized in this figure. This figure shows the values of the credit duration and credit amount in all of the counterfactuals. Each pair of points joined by a line is one counterfactual. The results show that the requested credit duration was changed in all counterfactual instances. In the original instance, it was 48 months. In the counterfactuals, it's between 33 and 12 months. The requested credit amount changed in 86% of instances. The original amount was 5,951. The counterfactuals take a range of values between the original value and 1,375. So the counterfactuals offer a large range of actionable options to the credit applicant, who can in principle choose the combination they prefer. To summarize this part, counterfactuals provide a type of explanation with a very clear interpretation. They address the right to explanation, in particular in the sense that they give actionable options for changing the outcome of the decision-making process. On a more technical side, they do not require access to the full data or model, only to the prediction function. One point that can be either an advantage or disadvantage is the Rashomon effect, which refers to the fact that counterfactuals typically do not provide a simple and unique explanation, but rather multiple possible scenarios among which the user can choose. This brings me to the end of this lecture and to the end of this series of 2 lectures on model-agnostic post-hoc methods. To summarize this part, we have reviewed some of the most important model-agnostic methods and we discussed their importance. The main strength of model-agnostic methods is that they can in principle be applied to any black box model. They moreover allow for explanation flexibility as different methods provide different types of explanations that meet different needs. We saw this in particular with counterfactual explanations. Model-agnostic methods also allow for representational flexibility, as they can use different features than the original model. We saw this for SHAP, but this is also the case for Lime. So, model-agnostic post-hoc methods are potentially a powerful way to generate explanations. It's important, however, to also mention some limitations. We started from this picture where post-hoc methods build an explainer on top of a black box model, which then produces explanations for the predictions of the black box. However, many of the methods that we discussed in fact do not work only with a black box model, but also require access to the original training data. So a more accurate picture would be this one. The original training data for a black box model is often not publicly available, so if an explainer needs access to the data, that is an important limitation. That's a first limitation of some of the methods we discussed. A second limitation is that for many of the model-agnostic methods, the algorithms that build explainers are not necessarily transparent and rely on some specific choices of hyperparameters. So sometimes adding an explainer might be similar to adding a second black box on top of the original black box prediction model. As a consequence, troubleshooting the whole pipeline can become complicated. If the explanations provided for an output do not make sense, it may be difficult to tell if the prediction model is wrong or if the explainer is wrong for some reason. Altogether, this underscores the importance of evaluating explanation methods, and this is a topic that we will discuss in the very last lecture of this course. But before turning to evaluations of explanation methods, in the next 2 lectures we will discuss another set of post-hoc methods, which are not model-agnostic, but instead specific for a particular class of prediction models, neural networks. Stay tuned and see you next time.